University. He is with the aerospace department. Dengfeng is a Berkeley alum. Go Bears. Let's try this. Go Bears! Bears. Oh, that's pathetic. Go Bears! We'll have to work on this. Dengfeng came to Berkeley in 2002 from Tsinghua University, I think with the Department of Control and Automation. He was first in the mechanical engineering department and graduated from systems engineering in 2007. Got a job from Purdue, but decided to stay a bit longer in the Bay Area. He worked at DASA Ames in the AFC branch. That's the branch that is working on air traffic control and air traffic management. And then joined the Department of Aeronautics at Purdue University in 2008. Was promoted to associate professor with tenure a few years ago, and since then has been working on a diversity of problems that initially involved large-scale traffic management with network modeling, and today have expanded to slightly broader scope with systems under uncertainty. So please join me in welcoming Dengfeng Sun.
Thank you, It's truly an honor and pleasure to come back here to Berkeley to see my advisor and to my former colleagues here and some former classmates. It has been a long trip back and forth, but I think I made it here today, and the weather isn't so good, but the environment is almost the same, encouraging and exciting. So today I'm going to talk about some of my research work on computational methods for optimization. In particular, we're going to address some uncertainties in the system by using change-constraint programming. And this is the work by my former PhD student, Jun Chen, who is now an assistant professor at San Diego State University. For those who are, actually for most of people here who are working on the ground transportation, so this is a very brief introduction to aerospace engineering. So this is the airspace. These yellow lines represent the centers. So there we have 20 continental centers in the US. Every center is basically an independent kind of unit controlling, managing the aircraft in their own domain. And each center is subdivided into several sectors, which are controlled by air traffic controllers. Usually we have one controller for each, responsible for each sector. I have been to several centers. Before that, I know there are some human controllers to these sectors, which I didn't know was that actually they are actually sitting in the same room and they talk to each other. So there is, when I thought there is going to be handoff between the sectors, like there's one aircraft coming from one sector to the other, I thought there is going to be some very advanced technology to do this kind of handoff, but in reality it's just pat on the shoulder, this aircraft is going to your sector. So it's a very interesting kind of experience, which also motivates me and our group how we can really do this in a better way, because this is really a human factor system and it's not really so autonomous or so advanced. We have a lot of technology nowadays to really automate some process in this system. So talking about the air transportation system, which might be a bit different from ground transportation in the sense that the weather plays a very big impact in the system. So this chart shows the delays caused for the Air Force flights, and you can notice here in this chart here, you can notice for most of the month, the delay caused by weather contributes to more than half of the total delays. And in fact, if you look at the whole year, there are about 60% of delays were caused by weather. And this is something I think we can do because this is a major contribution to the delays. If we can somehow manage this kind of delay, we can improve the entire system. As we studied the system, we noticed many times when you do the weather forecast, people usually say there is like 90% or 70% of chance there is going to be a storm somewhere, which is probability. So this motivates us. We can probably use some probability theory to do better things for the air transportation system. And this is the picture I took yesterday when I was flying from Indianapolis to San Francisco. And this happens quite often. You can notice here there are a lot of cancellations for the flights and a lot of delays right here. This is just one snapshot. This is all the departures from Indianapolis. You can see probably 1/3 of the flights are canceled. I'm not sure if it's due to the weather or due to some other reasons. Probably because of the weather, because there is very bad weather in the Midwest in the past couple of days. So this is the general kind of motivation, objective, and framework we have for this type of work. And this diagram here should be familiar to most of you here because this is some sort of control diagram. You have some input, you have a system. During my PhD with Alex here, I solved some deterministic models. So now I'm trying to introduce some uncertainties to the system and see how we can handle these uncertainties. And then my talk basically has this, includes these four parts. First, I'm going to introduce the chance constraint optimization framework. Then I'm going to talk about how we are going to use this chance programming technique to solve traffic flow management under some uncertainty. And then I'm going to talk about some computational work we have developed in our lab to really solve this problem, hopefully in real time. And then some work we are doing based on this type of work. This is a very abstract description of difference between deterministic optimization and stochastic optimization. So on the left-hand side, we have a general framework minimizing some objectives subject to some deterministic constraints. On the right-hand side here, we have some random vectors introduced in the system. So in terms of objective in air transportation, usually we have some cost of delays or delays themselves. Sometimes we will try to maximize throughput. Many times these these objectives are going to be either linear or quadratic or convex. And I'm going to explain why convexity is important in this study. And we have X as decision vectors. Basically, you can decide how many aircraft you can handle in a certain airspace and how much is going to be flowed to some downstream sectors because there are going to be some options. And there are going to be some other constraints such as the capacity of the airspace, capacity of the airport. And these capacities will be impacted by the weather. And there are some kind of random vectors. Basically, we're going to relate these vectors, these uncertainties to weather forecast. So this is the general kind of framework. In fact, there are a lot of researchers, including a lot of faculty here in Berkeley, who contributed a lot to this domain. For example, Professor Hansen and his students developed a scenario tree-based model to handle some probabilistic kind of situations for ground holding problem. So this is a very fundamental diagram for a scenario tree. Basically, start from some point at a certain situation. There is a probability, for example, there's probably going to be 60% of bad weather or 40% of good weather. And then you are going to study how things can change if you follow different branches. And at some other time, there is going to be some other possible events happen, either good weather or bad weather. So that's why it's binary. So, and you will even notice here, when you have a smaller time scale with few options of events happening, this is handleable. That's why they have Hansen has applied this to ground holding problem for a single airport up to certain hours. But you can also imagine if we want to handle a large scale system, if you have multiple airports, longer time horizon, this is going to be extremely difficult because, as we know, the scenario tree, the dimension is going to increase with these events exponentially. And once you have so many nodes, so many branches to handle, it's almost, because you have to basically enumerate every possible event, it is going to be impossible to do that computational-wise. On the other hand, there are some other researchers, it didn't show here on the slide. I have some reference here, such as Professor O'Donnell from MIT. They did some other approach. Basically, they do robust optimization. In this case here, they consider the worst case. They are going to guarantee their method is going to handle the worst case scenario for air transportation. if there is a storm, if the capacity is reduced to, let's say, 2 or 0, they are not going to fly airplanes. It's very conservative, but it is very safe. In the same time, the efficiency could be expectedly not so optimal. So in contrast to their work, what we do is here, we're going to have chance constraint optimization. So in this case here, we still have this similar type of constraint. Different from their work is we have some service level parameter, which is denoted as alpha. Basically, what we say is we expect like 90% of the time I'm going to keep my number of aircraft in this area to be less than the capacity. We allow, in certain cases, this capacity can be breached. Like you may have a few more aircraft over the limit. The good thing for this type of work is that this parameter here can be adjusted based on your needs. It's basically the balance between risk and performance. If you want to take more risk, you have to reduce alpha. If you want to have better performance, you have to reduce the alpha. In the meantime, if reducing the alpha could potentially increase the safety, the danger issue. And actually, when we first developed this model here, we didn't know what this alpha means. And then we talked to some people in business school at Purdue, and they say actually this is some kind of service level measures they usually do for their system. So in their system, the service level measures the probability that the customer demand within a given time interval will be satisfied without delay. Translating their words to our system is basically during a certain period of time, the traffic demand is going to be less than equal to the capacity we have in airspace or airports. And this, again, this parameter can be adjusted. Another thing which we didn't actually realize at the beginning is because for using the chance constraint programming here, we actually can consider joint capacity distribution because this is some reality. For example, the weather will impact a bunch of sectors. It's not staying in one single sector. Because if that's the case, we can actually reduce the chance programming to deterministic programming, which is pretty much simpler. And we actually validated this scenario using the airports in New York. So this slide shows the 3 major airports in New York City. Close to New York City, we have LaGuardia, we have Newark, and we have JFK. There's another one here, which is Teterboro. We didn't study this airport because we didn't get enough data for that airport. So when we do the study, did this kind of analysis for the delays or capacity for the airports, we thought that the Purdue students wouldn't know these airports because, believe it or not, many of the students in Purdue, they never left Indiana. That's one thing I was really surprised. But they do know these airports because if you recall, there was a movie, 2013, Sully, right? The pilot who actually landed in the Hudson River, right? That pilot was actually a Purdue graduate. So that's why Purdue students know these airports. And in fact, I asked a lot of students, undergraduate students, to work on simulators because I'm a pilot and I advise the pilot club at Purdue. I asked them to do the simulations. If that's really the best choice to land on the river, which is the part of the movie. And the conclusion would be, I wouldn't talk about here, but we can discuss later outside the park. It's quite interesting. Because we did a lot of simulations by real persons simulating using the simulators, and some of the students are really proficient playing those games, some are not. So I think we have enough kind of data to show if that's the best kind of decision. So anyway, coming back to this data, this shows the number of aircraft landed at those 3 airports, and we started the distribution here. And we think these capacities are actually correlated by looking at the covariance matrix. So in this sense, by using the chance constraint programming, we can actually handle the situation which is very realistic. The capacities of airspace are related. You cannot handle one single sector arbitrarily based by providing some probability single alone to this sector. Another challenge, again, didn't show the title here, is we like to have problem to be convex. There are a lot of reasons. First, for convex problems, the first order condition is necessary and sufficient. and the local optimal is global optimal. And if you are not familiar with convex optimization, I would recommend you take Professor Bynes' course this semester. Is it right?
127.
127. Okay, that's one of the best courses I have here at Berkeley. So we have a lot of tools to solve convex programs. In fact, in many literature, if you claim or if you can prove your system, your formulation is convex, you assume it is solvable. So that's a very nice thing. But if we introduce the chance programming properties in the formulation, you will notice the problem is not going to be convex anymore because the distributions are not going to be convex. And when we introduce these CDFs to the constraint here, the F here is no longer a convex program. The good news here is that, again, there is a reference here. Some mathematician proved if your distribution are log concave, you can actually prove the CDF is going to be log convex, which means this is actually by the mathematician Prikova, and who is Hungarian, and who unfortunately passed away about 2 years ago when we were working on this problem. So anyway, so if this random variable is log concave, we can prove the log of this CDF is going to be convex. So we can actually translate the constraint without loss any optimality or any kind of, without change the nature of the constraint, we still have a convex problem. So with this, we are going to continue. We're going to talk about how we are going to solve the problem using the convex approximation. Because your distribution, many times when you have the distribution right here, many times these are going to be sample points. You do not have a continuous distribution function many times. So what we do is we're going to use a convex approximation to approximate those distributions and put those functions in our constraint so we can solve them. And this is following some very nice work. We think it is based on some other researchers' kind of idea, but we really implemented it or realized in this scenario. So we try to do the approximation by a bunch of polynomials. And there is a type of polynomial which is called Boyne-Stein polynomial. The polynomials are going to be convex, and we're going to linearly combine these polynomials, still keep the convexity. And when we add all these polynomials together, we can actually prove the sum of all these polynomials arbitrarily close to the real distribution function, which means you are going to keep your constraint functions still convex. In the meantime, you have much better ways of handling these constraints because they are polynomials. There are a bunch of details here which is shown in the slide. So to do this, first we need to determine the overall error bound because it is approximation. Approximation naturally cause some errors, and there is going to be some kind of determining factor in the beginning how close you're going to do this kind of approximation based on these bounds. And given the bounds, we can actually compute a degree of the polynomials. This k is the polynomial degrees. And then we're going to pick k plus 1 number of points using the Chebyshev nodes. Chebyshev nodes, for those who are not familiar with Chebyshev nodes, they are the rules for Chebyshev polynomials. And this is just one of the ways of picking these points because, as we mentioned, many times we have the sampled points which might not be exactly these Chebyshev points, which is fine because as long as you have enough k plus 1 number of points, you can still do this approximation. Of course, if we use the Chebyshev nodes as we proved, you are going to reduce the errors in terms of approximation. Once we have these points, we can compute the coefficient Cj stars. This can be done easily by using either these squares, and in this case here we use the maximization. We use the minimization of their L infinity norm, which is much easier to compute. And with this, we can construct a bunch of these polynomials which approximate your constraint g of t, which is derived from your CDF of the distribution. And because they are polynomials, once you compute these polynomials, their derivatives come naturally, right? Everybody here knows how to compute the derivative of polynomials, right? Mm-hmm. My son even knows how to do that because he is only in 6th grade and he knows how to do the derivative for polynomials. So with this, we are confident we can convert our chance program to convex programming, and we can also handle situations such as correlated capacities, and we can adjust the service level measures to balance risk and safety. So the risk part is how we can put this to be useful. And in fact, before we did this TFM problem, we actually validated this same algorithm using the single airport ground holding program. And we had compared these two results. They are quite similar. So in terms of the traffic flow management, so this is, for those who are not familiar with air transportation, this is a very simple scenario. So suppose we have two flight routes, and suppose we have a intersection of these flight routes in a certain sector. Suppose the capacity is equal to 2. At one time, 3 of the aircraft wants to come into this airspace. So you have to make a decision which one is going to be delayed or diverted. So this is the fundamental concept of traffic flow management. And put this in a mathematical form, what we have here is we have an object function. In this case, we try to minimize the total flight time subject to a bunch of these constraints, such as the sector capacity number 1 here. You cannot have too many aircraft in a certain sector, and you cannot have too many aircraft departing at the same time or landing at the same time because the usage of runways, and you have some initial conditions, and you have conservation flows. And if we study these constraints together, you will notice some of these constraints are really deterministic because they are the nature of the physics, such as conservation flows. There's no stochasticity in this part, but there are a lot of things we can do in terms of the capacities. Those are things which can really be impacted by weather. And that's the part we're going to bring in some random vectors. And this is also makes sense in a lot of applications, such as number 1, as I mentioned, it could handle the weather. Number 2, because there are a lot of UAV activities in the US. In fact, it is predicted we are going to have about 7 billion UAVs in just the next couple of years. And we have known this in Purdue Airport because there are a lot of hobbyists and there are a lot of researchers who fly UAVs really close to the airport. In that case, that really reduces the capacity of the airport because it is used by some other vehicles. And there are some other operation uncertainties, probably due to the mechanical failure or even schedule of the flight crews. So that could also happen. All these things could possibly contribute to the uncertainties of the capacities you have in airspace, airlines, airports. So we first did a very straightforward case study. We can really compute the optimal solution and also compare to the result we have using the stochastic chance program. So this is a toy example, but this is a real case because we have a real airspace, we have a real airports, and we have real flights going through the airports. We actually have six flight routes, which is not showing completely on the screen here. And we have 5 sectors in the Cleveland Center. And this includes 4 airports, the Toledo Airport, Cleveland, Detroit, and also Erie Airport, the 4 airports. And we have studied, based on the history of the data, we studied what would be possibly the capacity, the distribution of the capacity in this diagram right here. And these are the real trajectory routes of the 6 flight path. So we validated our example using it's not showing here on the slide, it's called a brute force method. Basically, we are going to enumerate all possible capacity combinations based on this scenario. This is very time consuming, it's very challenging because here we have only a few sectors we can really handle that, enumerate that. But actually, if you have more than 10 sectors, you're going to have a huge number of decision variables. It's impossible to enumerate. But for this small case, we can still do that. So we study the result generated by the brute force, which is supposed to be the optimal solution because you enumerate all possible combinations and then compare that with our approximation, chance programming. So this is the optimal solution, which is basically all the flights is the base flight time for all the 6 flight routes is going to be 118 minutes. And based on our approximation, so we first relaxed the integer constraint because here you are going to fly airplanes, and airplanes are counted as integers. You cannot have 2.5 airplanes going to certain directions. You cannot split the airplane. So if we do this relaxation, meaning that you are going to have the floating number variable, so you can have like half of airplanes. If that's the case, the objective is going to be this 115.8 minutes, which is impossible, and it's also smaller than the best solution we have. Then we did the branch and bound on this solution right here. The result is going to be 122, which is reasonable, right? Because we are doing approximation, we are trying to be a little bit more conservative, and this result is slightly worse than the optimal solution. And in fact, we can prove, giving any certain approximation here, the suboptimal or the so-called optimality gap is always below 5%. In this case here, we have 3% of gap, and based on our mathematical analysis, if we choose the Boyne-Star polynomial to the degree of 15, we can guarantee that the gap is going to be below 5%. So that's the small case study. Basically, we validate our chance programming can produce a comparable result as compared to the brute force, the enumerating method. Then we try to extend this work to a much larger practical kind of size of network. So in this case here, we have used about 100 sectors. And for those who are not familiar with number of sectors, this is almost 5 centers, which covers almost one quarter or 1/3 of the entire East Coast. And among these 100 sectors, we picked some sectors in these 2 centers. So this is Chicago Center, this is Indianapolis Center. We picked a different number of sectors. Suppose they are going to be impacted by weather, because we know the weather probably will not cover the entire 100 sectors, but it's very likely that it will cover some of the sectors here. So we did different studies. We used 5 sectors to be impacted, 7 up to 20 sectors to be impacted. So that's the case setup. And the result is showing right here. So this needs a little kind of explanation. So what we did here is we have 5 case studies here. In the first case study, we have 5 sectors to be impacted by the weather. And in the fifth round, we have 20 sectors affected by the weather. And we choose different kind of service level parameter. The alpha parameter, if you still recall, probability of the constraints to be respected. In this case, we change different numbers, which is also reasonable because if we have fewer number of sectors, we expect the constraints, the hard constraints, could be respected easier because you have less number of constraints, right? But if you have more sectors, possibly with the capacity breach, the surface level should be decreased because you cannot expect you have too many aircraft, you have too many sectors. All the sectors are going to have very few number of breaches of capacity. So this shows how our algorithm works. And actually, we did about 10,000 Monte Carlo simulations for every case here. And you will notice here, initially, all these capacities are respected because you can see 100% guarantee the number of aircraft is going to be low. The reason is because you have very few number of aircraft in those sectors in the beginning of the simulation. And later on, as we call the steady state, which is shown right here, you can notice for some cases there is going to be some breach of the confidence level or the service level. For example, in this case, in the 15th sector impact case here, our service level parameter is 70%. So there are some cases there are probably at 71 or 72% of cases are I take back. So in some cases here, some of these, there are more than 70% of times the capacity is for the server's level equals to 70. It's supposed to be like under the number of times your capacity will be violated is less than 30%. You can notice here there are a few cases there are more than 30% of time the capacity is violated. That's the nature of chance programming. You cannot guarantee every time it is respected because it's chance programming. So this is the result for a 100 sector case. Covers probably about 5 centers. Then we try to validate if we really increase the size of the airspace, if we have more powerful computers, if we increase the size of the problem, is this algorithm still going to work? So this is the case we studied. So you will notice here the number of this so-called average gap is actually optimality gap. It's how your approximated method is going to generate a solution as compared to optimal solution. So you can notice here the gap is always around 5%. So if you have 5 seconds impacted, this is the chance. This is the optimality gap, about 3.5%. If we increase this to 20 sectors, it's still going to be around 5%. And you can, based on this study here, we are confident this method can generate reasonable, approximated optimal solutions, even you have a huge size of the network to be in consideration. And of course, to solve a large problem, you need to have a large, a better computational facility, which is our next topic, how we can carry out this type of work using advanced computational techniques. We actually had 2 students working on this project. One of them used the Hadoop platform, the other used the Spark. For the Hadoop, it is basically a bit outdated version, right, because it's earlier. And we noticed the biggest challenge for Hadoop is that it cannot optimally assign the jobs to different nodes. Look at this, the first chart here. Basically, if we solve like a 6 path of problems, you're going to decompose it into 6, right? And some of the paths are inherently more complicated, such as if you have a longer path, it has more states, it has more flying time. So their loads are going to be huge, much more than some smaller, shorter flight paths. In that sense, if you assign these computation solely to a certain node in Hadoop, it's not going to be balanced because overall, there is going to be a process to combine all these sub-problems together to generate the global solution. The combination is necessary, is critical, but they have to wait for every node to complete their own computation. So there is a need for doing the balance of the computation. And my student who worked on the Hadoop actually used a very simple PID control theory to balance these computational load, which is very hard, but the Spark automatically balances this work. So in my opinion, this work is more suitable for Spark because it automatically balances your different complexity of sub-problems. And this is the general framework. What we did here is the core part for doing the parallelization for computing is basically based on these polynomials. And these polynomials can be decomposed because they are, for one single constraint, they were actually a sum of a bunch of polynomials, right? Each single polynomials can be computed separately, as long as you can finally sum them together. So this correlation is based on the Boystein polynomial decomposition, and they compute the g of x, which is constraint, and the g prime of x, this is delta, the first derivative, because these are 2 things we need to solve convex programs. And here is the time, kind of computational time summary for the work we did. So we did a different number of computer servers, and we used a different number of threads to do parallelization. And you can see clearly there is going to be some reduction of computational time if you have more threads running on one server, which probably you have more experience than myself, because I know a lot of people here do the computation. But there is going to be some limit. Once the number of threads exceeds the number, there's not much benefit of doing parallelization. We did this experiment using 6 computers, and we solved 100 sectors. You can notice if we use 8 computer servers, actually if we use 6 computers, every computer has 8 nodes, 8 threads. Solving a 100-sector TFM problem for 4 hours, it takes about 10 minutes. And remember, this is generating the result for probabilistic programming with integer constraints. So these are really hard problems. And here is another study we did for computing time versus degree of polynomials. We noticed here, in fact, the degree of polynomials has a huge impact on the computational time. You can notice here, if your polynomial degree is over 25, it's going to be over a few hours. And we noticed that this might be a good balance. So, in reality, we think in our problem for optimizing traffic flows under uncertainty, I think the degree of 10 to 15 would be reasonable in terms of the computing. And because if you increase the degree of polynomials, you're going to reduce the optimality gap. Because if you have infinity, if the degree of polynomial is infinity, basically you'll have a perfect fit of the distribution function, right? Suppose it can generate exact optimal solution, but that's not computationally smart. So there is going to be balance or trade-off the accuracy and computational efficiency for this problem as well. Just to summarize what we did in this research, we formulated a trans-constraint program to take into account some uncertainties in air traffic flow management problem, and we designed a polynomial-based convex approximation to solve this problem, and then we also carried out this algorithm using parallel computing on Spark. So following this work, what we are doing right now is we are investigating the selection of the proper service level, which is the alpha. Because we talked this problem to FAA, and we try to see what would be a good alpha to be useful, to be meaningful. So far, what we did here is we just changed the alpha and see what's going to be our result, which is just a try and test kind of a process. But what would be the useful service level, we don't know yet. Particularly for this program, for this mathematical formulation, there should be some number which is going to be useful. And we also try to extend this kind of work to stochastic hybrid system, because we have some other Berkeley graduates who are faculty members at Purdue, Shanghai, and Insoc. They are doing stochastic hybrid system, and we think this type of work can be related to what we are doing right here. But the challenge would again be being the computational efficiency. If we use this type of work, how we can increase the efficiency of computation, or either from the perspective of algorithms or from the perspective of computing platform. And we are also trying to extend the application of this work to some other domains. So we are trying to use this to do UAV management, because as we know, the UAVs are usually of a smaller size as compared to our regular airplanes. Because the size of the UAVs, it is more subjective to uncertainties, which is, for example, the wind turbulence in the environment, which could be a big factor impacting the flight trajectory for UAVs. So that's all I have for today. Any questions? Yes.
Two questions. So first, just follow up on your UAV, this vision on UAV. So what will be the air traffic control structure for UAV? Are the radar going to be also sector-based, so it's a different structure?
I think that's, yeah.
Second is for one of the slides on this flat tree, the evolution of there are different curves representing number of sectors affected over time. So can you explain why in the beginning there are lots of fluctuations and then
Even here?
starts? Yeah.
To answer your first question, I don't think there is either policy or regulation to study the UAVs. Is that your question? To either separate them from operations of the commercial airplanes or the general aviation airplanes? I don't know, because there is a debate if they should coexist in the same airspace or they should be separated. There are different studies such as the geofence separating the two operations. So in that regard, I'm not quite sure. But that's going to definitely that's going to affect the operations of the airplane, right? Because if you either do the coexistence of UAVs and the manned airplanes, they're going to use the airspace capacity, right? If you want to separate them, you're going to reduce the size of your airspace. So either way, they're going to affect your airspace capacity to some extent.
How about just applying the model to UAV TFM?
So if we want to use this model to handle UAVs, I think it can handle UAVs to some extent, such as the trajectory planning. But if you want to consider the UAVs as part of the management of the air traffic flows, there is going to be a lot of study we have to work on, because UAVs are not only using the airspace facilities, right? They are going to, sometimes people think they are going to actually improve the system, such as the way the autonomous vehicles improving the ground transportation, right? There is going to be study for, I think there should be some similar study in the air for this type of work, but we didn't take a look at that part yet. Right. Your second question for here is, so for this part here, I believe the reason we have here is because initially, based on the setup of our problem. So for example, if you come back to this toy example here, you will notice we intentionally put a lot of aircraft in this. So this aircraft is going to meet each other early in the stage, such as a couple of minutes or 10 minutes, 20 minutes. They are going to meet in certain airspace. So that's why after a few times here, there is going to be something that's really out of control. Because you let the aircraft depart, you didn't delay them on the ground, so just let them go into the air and see what's going to happen, right? They could be possibly delayed in air in the first couple of sectors, but those couple of sectors could potentially be used by some other trajectory routes. So at some point, the airspace is going to be congested. And later on, we are going to dispatch all these aircraft into different sectors, so the system becomes sort of balanced.
So this horizontal
this is the time, right?
Is a modeling period.
Right. So this is a 2-hour kind of example right here, right? Because after 2 hours, they are pretty much similar to the curve right here. Sure. Yes.
Can you go back to the slide where you have the optimization formulation and constraints that have the random variables?
Here?
So, yeah, I guess I want to make sure I understood something. So here you're interested. What's random here is these C's, these big C's.
I would say it's not exactly C's, it's the probability, how these constraints will be respected. It's really the part, the formulation right here. I forgot where the slide is. Basically, you have a constraint here, right? There is a probability this constraint will be respected. There is a chance, this like a 90% chance this constraint will be respected. It is related to the uncertainty of the capacity, but it's not directly. The capacity is a random variable. It's not a random variable. We formulate the deterministic constraint as a probabilistic one. Check if I have this. I should have the slide here somewhere. like this here, right? This is a deterministic kind of constraint. And then we put a probability such that this will be respected by this much of chance.
Yeah, so the reason I'm asking this is because I'm trying to understand if your inequality constraint is linear in the optimization, is jointly linear in the optimization variable and the random variable, okay, that is, they don't combine in a nonlinear way.
No.
Then to finish my sentence.
So once you introduce the probability, there is going to be the probability distribution density function, right? That is nonlinear and that is coupled.
No, I mean the inequality constraint. I'm trying to understand precisely how your random variable appears and why you need, when you do this approximation, why you need it convex. I was just trying to sort out those details.
Oh, okay. So I think that you have to plot this slide right here, right?
Yeah, so for example, what is the relationship between z and x?
Z into C?
No, z.
Z, okay.
Yeah.
So the Z here is actually really write x, or Z is actually a function. So it's basically it's basically the probability of G less than or equal to Z. So that's F right here.
Okay.
It's just a reformulation of the problem.
Is z a function of x?
In our case here, Z is not a function of X, such as Z is the capacity of your system, of the airspace. So if we come back to the actual problem we are solving right here, you can consider this Z as C, right?
Okay.
C as X in this case here.
Okay, C, xi is, I can think of those as being the big C's here.
Right,
Okay.
right.
And then z,
X,
okay.
yeah,
Okay, z would be like x here?
right.
Can you go back to the other slide? One more. I'll use Z, like you're going to use.
Yeah, thanks.
But so, I was wondering then if Z is a, so are you saying Z is a parameter like the C?
In this case, it's actually an operator. It's an inequality. So there is, I agree, there is some kind of confusion regarding notation here. So Z here is basically it's an inequality. It's an operator. It's a constraint.
Z is a constraint.
Yeah.
Okay.
Right.
And when you say it's an operator, you mean it's an implicit function of X?
It's explicit function of X.
Explicit function
Right.
of X.
Right.
Okay. Okay.
So that's why you can solve for example if that's a single variable, univariable kind of problem, you can solve based on the probability. You can solve for X, right? In our case, we couldn't because it's joint probability.
I see. And it's not an explicit function, I assume, because otherwise you would have.
Right. Yeah. Sure. Okay. I think I misunderstood your question. So we cannot have a closed form of the solution for X in this case. Because it's joint probability, right? You have multiple variables.
Okay.
Any more questions? We just want to thank you so much for coming out on behalf of ITS Berkeley and Transoc. Here's a branded water bottle, and we really appreciate you being part of the seminar.
Thank you very much.